Hey guys, welcome back to Bottom-Up Chem, and we're getting into the nitty-gritty now. Yeah, that's right, we're getting into the good stuff. We're looking at Ka and Kb calculations. This lesson is going to be example and calculation heavy because I think that's going to be the most useful way for you to learn this. As always, if you comment below to suggest new content, let me know how you feel. Like, subscribe, and hit the bell icon. And please share this content, share the channel, and check out our other videos and our other channels. Anyway, on with today. We're looking at Ka and Kb calculations. We're going to define what these things are. We're going to look at how the strength of an acid can affect these values, and then we're going to get into some juicy calculations. First, got a little refresh question for you, which is a paper 1 question. Which of those statements are correct for a 0.01 mole per decimeter solution of NaOH at 298? Pause the video here to give yourself some time for that. So easiest way for us to get started here is going to be to find our pOH, because we know that we have a 0.01 mole per decimeter solution of OH minus ions. So that is going to give us a pOH of 2. We can then use the relationships between pOH and pH together to find the remaining information that we need. So we know pH plus pOH is 14, and that we know OH minus and H plus concentration is 1 times 10 to the minus 14. From the information we already have, we know that C and D are not the correct answer, and we know that already our OH minus concentration is 0.01, so it can't be B as well. Therefore, the answer must be A. Okay, so now we can introduce Ka and pKa. So we already know that weak acids and bases are different from strong acids and bases because they form this equilibrium, which lies mainly over to the left-hand side. So instead of just having our 2 product components, we also still have some HA present. But we can still write an expression just like with Kw for our equilibrium constant. Okay? That's going to be this Ka, which is going to be H plus times A minus over HA. So in this way, it's even more like unit 7 than the Kw value was, because we don't remove that HA from this equation. We're going to keep it in there because it's relevant for our calculations. Just like we did with Kw, we can also take the logarithm of this and give ourselves a pKa value. So now we have pKa, pOH, pH, pKw. All of these, that little p, just remember, is negative log of whatever is after the p. Okay, let's just put these ideas alongside what it looks like with a base. So we can see that for bases, it's exactly the same. We have B plus OH minus divided by BOH. And to find our pKb is exactly the same. We take negative log. A smaller value of Ka or Kb indicates a weaker acid or base. Okay, now that makes sense when you look at the equation, because if you look at the equation, we have the HA and A minus on top divided by the reactants HA. So a smaller value indicates that there is a larger concentration of the HA, which means that the equilibrium lies over to the left-hand side and therefore is not a very strong acid. So just using your equilibrium knowledge to apply there. Now, if we take the pKa or the pKb, this relationship gets inverse. So a smaller pKa indicates a stronger acid. So just remembering the difference in order of those. Now, these acids and bases at the bottom, you don't have to remember these. They're just there for reference in terms of this slide. You actually get a lot of that information in the data booklet. So you don't need to remember those, but you do need to remember the relationships up at the top. Talking of which, let's test you on that. Write the equation to show the dissociation of weak bases in an equilibrium. Pause the video to give yourself some time for that. Pop them up. Good. Hopefully you got the BOH for a generalized base goes to B plus and OH minus. Building on that then, deduce the expression for the equilibrium constant of a weak base. Pause the video here, give yourself some time for that. Pop them up! Okay, and just like it always has been, products over reactants B plus OH minus over BOH. Okay, building on that further then, how can we calculate pKb? Give an equation for that. Pause the video to give yourself a moment to do it. Pop them up! And hopefully you got taking the negative log. So this brings us to a point where we have a lot of different terms and a lot of different relationships now. We've already looked at pH and pOH, and now how to calculate Ka and Kb, which leads us for pKa and pKb. Now, these fit into the relationships that we've already established quite neatly. Remember Kw, and so now we can say that Ka times Kb is equal to Kw. Further to that, if we take the logarithm of the Kw equation, just like we did before, then we're going to get pKw equals 14, but that's also going to be pKa plus pKb equals 14. So the relationship kind of mirrors that of our H plus and OH minus concentration that we already looked at. And that's that equation just at the bottom I've also included there. So these relationships are going to form a key part of our understanding how to conduct ourselves in calculations, and also how to conduct ourselves in novel areas where we may not understand exactly, or it doesn't look like a question we've seen before. If we can use these relationships effectively, then even if we don't take the most direct path to the answer, we should be able to formulate an answer. So I'm going to go through 4 of the main kinds of questions, and maybe one other question at the end that you'll find in exams, but this is not an exhaustive list of the type of questions that you can be asked. The point is here we want to develop a capacity to understand these areas, to manipulate these equations and relationships and apply them. So let's have a look at a question calculating OH. So here we want to find the concentration of OH minus ions in a weak base. So first thing I'm always going to do is I'm always going to write out the equation if they don't give it to me. That's just going to make things a lot easier. And then once I have the equation, I'm also going to write out my expression for Kb. These are almost always going to be used, and even if they're not going to be used, they're certainly going to ground you in what you actually have to do, not including H2O there, as it has a value of 1. So we're going to make a couple of assumptions as we go through this question. One of these assumptions is that basically this equilibrium actually lays almost completely to the left-hand side. If you look at the Kb, then we know that the actual number of the concentration on the right-hand side is going to be super low. And because of that difference in concentrations, we can assume that the concentration given to us in the question is the concentration of our NH3 in the bottom of this fraction. Now all I have to do is I just have to start plugging my numbers in. So I've been given the Kb, which is 1.8 times 10 to the minus 5. And because the equation is 1-to-1, just like with Kw, I can say that the concentration of OH minus is squared. I could also say the concentration of NH4 is squared, but this works better for our calculations. And I also put 0.5 on the bottom of the fraction from the concentration given to us in the question. Then we can see that all I have to do now is multiply through by 0.5 and then square root the whole other term, and then that is going to give me my OH minus concentration. So I'm going to get OH minus is equal to 1.8 times 10 to the minus 5 multiplied by 0.5, all square rooted, and that comes out to 0.003 moles per decimeter. And for lots of questions, that will be the end of the question. However, I've added this percentage of dissociation just because I've seen this question a few times and I want to give you a walkthrough on it. So here it's asking us how much of the NH3 actually dissociated. So to work out percentage dissociation, I'm just going to take my concentration that is at equilibrium and divide it by the concentration of the solution. So I've worked out my concentration of equilibrium, which is 0.03, and my concentration of my solution is 0.5. That gives me an overall of 0.6%, obviously indicating heavily that we are laying to the left of the equilibrium, which I mentioned earlier. So not too difficult once you know how to do it. Let's get you doing a question, but one that doesn't include the percentage dissociation, just calculating the concentration of OH minus ions in a weak base. Pause the video here to give yourself some time for that. Pop them up. Okay, so again, first thing I want to do is write out the equation if they don't give me equations, just so I know what equation I'm dealing with. And I'm also going to write my expression for KB because I'm always going to need that when I'm calculating this. Again, we're making the same assumption as before, which is that the equilibrium lies really to the left-hand side. And so that 5 moles per decimeter is the concentration we can use for NH3. And then we just plug in our values to this equation, remembering that we can make OH minus squared because those two are equal in that equation. Then I'm just going to multiply through by 5 and then use square root of the whole thing, which will give me OH minus equals the 1.8 times 10 to the minus 5 times 5, all square rooted, which gives me 9.48 times 10 to the minus 3 moles per decimeter. Okay, let's try another question where the kind of special ability or special twist is our dilutions. Once again, always going to start by writing out that equation. It's just going to make it so much harder to mess things up by accident. So I write out my equation for the dissociation of the ethanoic acid, and then I'm going to write out my expression for Ka. So remember, it's products over reactants. And here you can see that I wrote it with the H3+, but then I'd have to include water underneath. So it's perfectly okay to write this either way, you know, it doesn't matter. I've just now switched that to H+. So again, we know that it's going to lay over to the left-hand side. So our concentration of ethanoic acid is going to be the value we use in the bottom of our fraction, and Ka is the value that we use for Ka. Now remember, we're going to make our two products equals to each other and then just plug in our values. So now I get 1.74 times 10 to the minus 5, H plus equals H plus squared over 0.1, multiply through by 0.1, and then square root that whole term to give me my H plus equals 1.74 times 10 to the minus 5, multiplied by 0.1, and that whole term square rooted. And that equals 1.32 times 10 to the minus 3. So to get our pH, we just do minus log of that value, and that gives us a pH of 2.87. Now the question asks us what will happen with a 10-fold dilution. So common mistake here is to just divide that by 10, but that's incorrect because that doesn't account for it being a weak acid. So what we actually have to do is we actually have to change the concentration we initially put into that equation. So for this, it would end up looking like 1.74 times 10 to the minus 5 divided by 0.01. So just be careful in these questions that you make sure you go back far enough in the question to change the concentration of the initial acid, not the H plus concentration. You can divide the H plus concentration if you're using a strong acid, but here it's a weak acid, so we have to change it initially and then go back through our calculation again. Anyway, that gives us 4.17 times 10 to the minus 4, which gives us a pH, the minus log of that value, which is 3.38. Now, what we see here is a change in 0.51 pH, which is what we'd expect. Remember, looking back, the properties of weak acid is it's going to change more slowly to the addition of a base because it's not fully dissociated, unlike a strong acid or base. Okay, let's get you cracking on a finding pH question. I've removed the dilution component from this one just to get you going. Here, you're finding the pH of a 3.25 mole per decimeter solution of ethanoic acid. I've already written the equation out for you. Pause the video here to have a go at that. once again, if I've already got the equation, I'm still going to need my expression for Ka. So I'd always start with the expression for Ka, and remembering that this is going to lie over to the left-hand side of the equilibrium. So the concentration of ethanoic acid given to us in the question is going to be equal to the concentration in the Ka expression. And we're also going to make our two products equals to each other, so we can make it H plus squared or H3O plus squared, whichever you prefer. Plugging that all in, then we get 1.74 times 10 to the 5 minus 5 H plus squared over 3.25. Then we rearrange to find H plus, so we're going to multiply through by 3.25 and then take a square root of everything that's left to give us H plus equals 1.74 times 10 to the minus 5 multiplied by 3.25, all square rooted, and that's going to give us our H plus concentration, which is 7.52 times 10 to the minus 3 moles per decimeter. Obviously it's asking for pH, so take the negative log of that value we got for our H plus and we get 2.12. Fantastic. So let's have a look at another example, maybe slightly more advanced, looking at finding Kb from pH. So in this question, I've got a 0.035 solution of methylamine and I have a pH of 11.59. And it wants me to determine the Kb of methylamine and the Ka of the methylammonium ion. The question made our lives slightly easier in that it gave us the equation and the expression for Kb. So the first thing I'm going to do is work out my pOH. So I'm going to take the nice easy route and do 14 minus 11.59 equals 2.41. This allows me to easily find my OH minus ion concentration by doing 10 to the power of minus 2.41, which is 3.92 times 10 to the minus 3 moles per decimeter. Now, unlike the previous question, we haven't been given our Kb value, but we can still do what we did previously, which is making the OH and the methylammonium ion equal to each other in the Kb expression, because we assume that the equilibrium lies to that left-hand side. So we're still making that assumption. So that means we can say that OH minus has that concentration and so does the methylammonium. And that means that when we plug that into the calculation, we can write that as 3.92 times 10 to the minus 3 all squared over the value of 0.035 moles per decimeter of the methylamine is going to be equal to my Kb, which is 4.39 times 10 to the minus 4. So we've got 1. At this point, we've done most of the heavy lifting, so now we can just use the relationship Ka times Kb equals Kw, rearrange to find Ka, which is Kw over Kb, plug in 1 times 10 to the minus 14, divided by the value we just found. It's going to give us our value for our Ka, which is 2.28 times 10 to the minus 11. And we bossed it. And really, the calculations that we've actually done are exactly the same, except we've changed focus in the Kb equation of what we were trying to calculate. And then we're just using those relationships that we went over at the beginning of the lesson. Now, I'm not expecting you to know those right now. They might be useful to have written down and to have alongside while you're doing these questions, and you can learn them over time. But they are very useful. So let's set you loose on one of these. Here's a question. 1 mole of phenylamine has a pH of 9.31. Determine the Kb of the phenylamine and the Ka of the phenylammonium ion. You've got the equation, you've got the Kb. You can do this, guys. Pause the video here to give yourself some time to do this. So, just like before, I'm going to use what they give me. They give me the pH, and I really need the pOH. So I'm going to do 14 minus the pH to give me my pOH. So that's going to be 14 minus 9.31, which is 4.69. Now from that, I can do 10 to the minus 4.69 to give me my OH minus concentration, which is going to be 2.04 times 10 to the minus 5 moles per decimeter. Again, I'm going to make the same assumptions. Because it lies over to the left, 1 mole per decimeter is my concentration that I'm going to use for my phenylamine. I'm going to make OH minus and the phenylammonium ion the same concentration. So that means I can use my value for OH minus all squared divided by 1, which is the concentration given to us in the question. And then that is going to equals 4.17 times 10 to the minus 10. Again, that's your heavy lifting done. Because to get your Ka, we can just use that relationship Ka times Kb equals Kw, rearrange to get Ka, Kw over Kb, 1 times 10 to the minus 14 over 4.17 times 10 to the minus 10, which gives me a Ka of 2.4 times 10 to the minus 5. Now I have my Ka and Kb. You're done now. Hopefully after this, you're starting to develop a little bit of the understanding of the relationships between these, and if not, you will with more practice. Let's try one where we're looking at calculating the pH after a neutralization reaction. So here it tells us we had a concentration of volume of NaOH that reacted with a concentration of volume of ethanoic acid, and it wants us to tell us the pH at the end. So I've got a strong base here, so I'm just going to calculate my number of moles of base. So I can do that by taking the volume and concentration, multiplying them together to give me 0.02. I'm going to calculate my number of moles of ethanoic acid, which is going to be 0.8. I'm going to take the smallest one from the largest one to give me 0.78 moles of ethanoic acid remaining. So this is the key part of this question. This is what differentiates it. We have to find out which one is left over and how much is left over. So we've just found out our number of moles of both and then subtracted the smaller one from the larger one. Once we've done that, we can find the concentration of the remaining solution because we found the number of moles. Now we add the two volumes of the overall solutions together, which is going to give us 1 decimeter, and then we're just going to do moles divided by volume, which is 0.78 divided by 1, which equals 0.78 moles per decimeter. At this point, the question comes exactly the same as the first two we did. Now we're just going to use the equation for Ka, plug in all the values we have. So remember, we can make H plus and the ethanoate ion equal to make H plus squared. Then I'm just going to rearrange to give me 1.74 times 10 to the minus 5 times 0.78 all square rooted, which gives me a H plus concentration of 3.68 times 10 to the minus 3 moles per decimeter, and I just take the negative log of that to give me my pH, and that gives me a pH of 2.43. Yeah, we're cooking up a tasty broth. So let's get you doing this. Similar kind of question, using NaOH and ethanoic acid. Equations are given to you. Take your time, don't rush, try and apply the ideas that we've gone through so far. Pause the video here to give yourself some time for that. Okay, let's go through this question bit by bit. Remember, first thing I want to do when I've got a reaction going on is find out how many moles I've got left over. So I'm going to find my moles of my hydroxide ions, which is going to be 0.075 moles. And then I'm going to find my moles of my ethanoic acid, which is going to be 0.25 moles. I'm going to subtract the smaller one from the larger one, which gives me 0.175 moles of ethanoic acid remaining. I'm going to add those volumes together. Remember, don't forget that step, which is going to give me 0.65 decimeters. Then I'm going to find my concentration by doing 0.175 over 0.65, and that gives me 0.269 moles per decimeter. From there, all you're going to do is you're just going to plug that into your Ka equation, making H3O plus and the ethanoate ion equal, which gives you H plus squared over 2.269. So you can do H plus concentration is equal 1.74 times 10 to the minus 5 times 2.69 all square rooted, which gives us a H plus concentration of 2.16 times 10 to the minus 3. And then we just have to take the negative log of that, which will give us our pH, and that is 2.66. Lovely jubbly. Right, so I'm going to just do one more example of bringing these relationships all together. This is just going to be an example. Here we've got benzoic acid, and the question asks us to find Ka, Kb, and pKb. So this question is supremely about knowing the connections between these different terms. And I'm going to start us off here with Ka. And as we'll see, that isn't where you would have to start, but that's just where I'm going to start. So we can get Ka by doing 10 to the minus pKa, which is 10 to the minus 4.2, and we get 6.31 times 10 to the minus 5. Okay, where can we go from there? Well, we know that Ka times Kb is equal to Kw, so Kb therefore is Kw over Ka, so I can do 1 times 10 to the minus 14 divided by 6.31 times 10 to the minus 5, which gives me 1.58 times 10 to the minus 10. So now I've got 2 of the 3 from the questions. So I've got my Kb, I've got my Ka, and I can take the negative log of Kb to find that, or I can use the relationship of pKa plus pKb equals pKw. So pKb equals 14 minus the pKa, which equals 14 minus 4.2, which is 9.8. And really, the reason I've given this example here is so that you can try and connect with the idea that if you didn't have a calculator to do negative log of what the Kb was, that you could actually use those relationships to do it without a calculator, or even if it's not about calculators, that there are many different ways which you can approach a problem. And that, I think, should be a liberating feeling. That should mean there's not one way, there's not the way I did it and that's the correct way. The more you understand these relationships, the more you'll be able to determine your own path. Even if that's the long route, if that helps you develop the skills, then that's down to you. You don't always have to take the shortest path. So as long as you're looking at those relationships and your key assumptions, then you should be fine. Just remember, it's as important as ever that you really do a lot of questions with this so you get familiar with all the different types of questions that you could be asked. Thanks for watching, guys. Comment below, like, subscribe, hit the bell icon, share the channel, and check out our other videos. Appreciate all the feedback and support I've been getting. As always, practice makes slightly better.